Well, I'm what's standing between you and lunch, so I'll try to keep you entertained at least till then. I'm going to talk about a really exciting topic called calibration. I know you're... I will say, though, that I do find it exciting, and people that know me will know that I like math, so this is right up my alley. Okay, so what motivates us to do calibration? We are interested in fielding systems in factory environments. So when you put cameras around the scene and you're trying to track objects in the scene, or if you're putting cameras on, or 3D sensors on robots, we need to know where they are, and when the maintenance guy comes through and bumps the camera or does something, we have to be able to have people in the factory without an engineer get back to the calibrated and working condition. So we need to have a push-button intrinsic and extrinsic calibration that is consistently accurate and provides good results. So we are, along that lines, we're developing a sort of a unified framework that does all kinds of calibrations. And the main difference in the examples you'll see are that we just changed the script that runs the calibration that decides which type of thing it's going to be doing. So we want to essentially automate the collection of the data, and then also that involves moving the machinery around and collect the data, and then solving for the solution, and then updating the models that control how things interact. Okay, and our current package includes an extensive set of these cost functions. You've heard of those earlier today. I've got lots of those too. We have some examples and some tutorial material. And I will say at this point it's all a work in progress. You can access it and look at it and try it out, but be aware that it is still very highly experimental. Okay, so our calibration tasks include extrinsic calibration. That means finding where the cameras or the sensors are in the scene. We might have an array of those cameras that are looking down on a mobile robot and we're tracking its position, or we may have an array of targets out that are fiducials that we're tracking from a camera that's on the robot. We want to know where those targets are and how do you calibrate that aspect. We want to calibrate robots. Where is the robot relative to the cameras? And we might have a camera mounted on the robot, and again, we have some kinematic model of where it is, but it's not always accurate. So we need to be able to determine that more accurately. And soon we'll be having facilities that will do intrinsic calibration and stereo calibration, and ultimately we'll be able to do kinematic calibration of the robot. Okay, so how does this all fit together? We have envision, somebody's got this killer app that allows them to scan a bunch of parts going into a paint booth and have the robot automatically paint them. So they're talking to move it, and so all the blue objects are sort of standard stuff. You've got a robot and a joint state publisher that's keeping track of where everything is. All that is powered by some Zacro file that generates your URDF. However, all the items in those Zacro files, or your URDFs, for where the cameras are typically static. So how do you have your calibration routine, which are the things in the red, how does that change your model so that when you start it back up again, everything is essentially calibrated? Okay, so what we have done is we've modified the thing in the yellow, which is your Zacro file, slightly to replace every calibratable thing. Like that's where the tower is that all your cameras are attached to, or where your robot is. We exchange every calibratable joint with a sequence of joints. So we have a little macro that we add to that in place of every joint that you want to calibrate. And then along with that, we have to run this new object or new node called a mutable joint state publisher, which simply just publishes the roll, pitch, yaw, X, Y, and Z for that joint that allows you to change it. And then we run the calibration, which collects all the data and then calls the services of that mutable joint state publisher and allows it to update it. But it updates the values by writing them to a calibratable joints YAML file. So basically, when you after you run it, it changes the YAML file. Then you start your system up again if it goes down, and all the calibration results are visible. Okay, so to show you an example, we have a Motoman robot, and I'm going to talk while this is running. The interesting things that you should note are that we have a ASUS sensor that is mounted, and it's not even touching the robot. So we don't know exactly where it is. We don't know where the camera is on the robot. The target is also just laying on the floor of the robot's work cell, and so we don't know the transform from the robot to the target, and we're collecting through this little script where we push the button and say calibrate, and it talks to the robot, makes the robot move. It's using Move It to do that. It's collecting a whole bunch of images, and you can see, I had this laser that actually worked. Up in the right-hand corner, there are a circle grid pattern where it's finding with each motion. So it moves the robot over, takes another picture, moves the robot, takes another picture. And then at the end, it's going to calculate both where the target is relative to the robot, which we really don't care about. We just threw it on the floor. We just wanted to figure out that, and where the camera is. Okay, and it's important to note that the set of images that you collect have to be rich enough in order to define where both the target and the camera are. If we took all the images just by moving in a plane, we could then imagine moving the camera a long ways away from the robot, attaching it with a really long lever, and then also moving the target in that same direction, and we'd get those same images. So we have to make sure we get the target from all kinds of different angles, and so that's what's going to happen. If we saw the actual video of the robot, which I think was online somewhere, you can see that the robot moves way over to the side and takes pictures from all different angles in order to run this. So it runs as a service call, and it's sort of running sort of in the side of your system. I'm waiting for it to finish collecting. So it's finished collecting the data, and now it's running the calibration. This is all just taken screenshot live. And what it's doing now is it's adjusting all the transforms by calling the services for that mutable joint state. And now they're all updated. And you can see now that the camera is more or less where it was mounted on the robot. And the target, which is the 3D, or the planar grid of points, is now no longer lying down inside the table, but is right side up. And in fact, the 3D data from the ASUS sensor, that point cloud is laying directly on top of it. Okay, and I think I already covered the key aspects. We're interfacing to move it, to do the planning and execution. So we're moving each joint state that we tell it to go to. It's planning a collision-free action between them. We have to collect the sufficient geometry in order to get a good calibration solution. We interface to TF in order to measure where the robot thought it was at each point. And the result is we compute the two 6 degree of freedom transformations, both to the camera from the tool point and from the robot base to the target. And then when we're all done, we get a consistent set of 3D data from the robot, from the camera using the robots. Now we can move the robot all around and collect point clouds, and it'll all be registered to one another automatically. Okay, so how do we do all that? So there's a quick primer on calibration. We are essentially maximizing the consistency of the collection of observations with the physical model of those observations, and that's essentially minimizing the sum of squared error of the reprojection error. Okay, so this reprojection error is we think we know where the point was in space. We think we know where the camera was. We project and predict where that point would show up in the image. We also have an image. We compare the two, and that's the error. Okay, so that's basically what we're doing. We have a sum of squared errors from all the observations, should be minimized, and then if our model is correct, if our camera is in the right spot, and our target is in the right spot, then the errors will be as small as possible. Okay, so the difference in all our cost functions is what is known and what varies. In other words, if we have a printed target, printing errors will show up in the positions of the target. Let me show you this. So the little yellow dial there was meant to indicate that sometimes we want to calibrate the target. We want to know what are the printing errors in the target. Sometimes we have a intrinsic calibration that's not done. So we have a little yellow dial over there for the distortion model of the camera. So we're trying to calculate the parameters of the intrinsic parameters of the camera. In the example that I showed, the transform between the reference frame, which is the base of the robot, and the target mount, which is the end effector, that is known. In this case, we would use, in the cost function, it's passed in as part of the constructor, whereas the transform from the base to the target is unknown. So those are parameters that are adjusted by the optimization procedure. So essentially, all the different calibrations that I can think of include these more or less 5 different coordinate frames, and basically projections or transformations between all those frames, and just all the different combinations thereof that you can think of for your calibration that you're trying to do. Okay, so in some cases, the robot might hold the camera and look at the target. In some cases, the robot might hold the target while the camera looks at it and put it in front of it. Okay, and basically you can write a cost function for any situation you want, and I've written the library that I've written includes a whole variety of them, and it's a matter of figuring out which one you want to use for your task. Okay, so how does the calibration process work? We have a YAML file which defines the cameras, one which defines the targets and all the information about the targets, and one which defines all the observations you're going to make, and that includes a sequence of static scenes. So for each static scene, we send out a trigger. Now, the scene trigger is where we move the robots. So we've implemented this generalized thing called a scene trigger, and one of the scene triggers we implemented was a interface to move it, which basically says go to these joint values. So in your YAML file that's saying here's the calibration I want to do, you just say, oh, I want a robot scene trigger, and these are the joint values I want to go to, or here's a robot scene trigger, and here's the Cartesian location I want to move to. And when the calibration procedure is being executed, it simply says, okay, the first scene, I need to call this trigger, and the robot will move. When it's done, then the observations are allowed to occur, which is that when it's done, it collects all the transformation information that's required. So now it asks, where is that robot? Where are all the known things? And then it collects the images, finds all the targets that it was asked to find, and it sort of does all the bookkeeping that's necessary to pass that into the cost or the reprojection error function for each of the different circles it was looking for into the series solver. Okay, and then the series solver simply says problem.solve, and it goes through and adjusts all the parameters, or the variables, I should say, using all the information that's been collected, and then outputs the results by setting and storing the information in the mutable joint states publisher, and then writes any static transform publishers that it was required to write, and you have the solution. Okay, so what's special? First of all, series, if you haven't used it, is the best optimization procedure ever. Those guys were geniuses that made that, mainly because it computes the Jacobians, which are basically derivatives of these cost functions, analytically and automatically. Anyway, I can't say enough about how nice this package is. What else do? We have these scene triggers which tie into Move It, which allow us to coordinate motion, allow you to say, to tell the operator, you need to hang the target now, and then hit return so that we know that it's ready to go. Those kinds of things. We have camera observers that are already designed to find circles, circle grids, and checkerboards. Obviously, we're using standard libraries for those things. We have transform interfaces using TF. We make a lot of use of that. And we have these mutable joint state publishers, which allow us to see the results immediately and then have them persist after the calibration routine is no longer running. And then finally, we have this library of, I'll call them series compatible projection cost functions. And what 93 means, I don't know. Okay, so another thing that's special that a lot of people don't know, and this is just a tidbit of information, is when you have a circle grid, and I've seen a lot of people do this, and I've done it before, you're trying to do intrinsic calibration, and so you hold your target up and you move it around and you get all, and you take a whole bunch of pictures all over the image, and they always tell you to hold it at a skew angle. Well, here's an example where I have on the far right-hand side, the little angle is the edge view of a circle, okay? And so you're viewing that with your camera on edge. Well, if you notice the center of the circle, which is halfway between, well, it has the letter A indicates that both sides are the same, is shown at the middle between the line segments B and C, and the image on the image. If you'll notice, B is not the same length as C, so the center of the circle is not the same as the projected center of the ellipse that you see in the image. So when you hold your target to the side, all your centers get shifted. Okay, so our cost functions take that into account, and most calibration routines don't. So this is a small difference. So if you're using the circle grid and the OpenCV calibration, always hold your target pointing straight at the camera. Okay. Okay. So what are the best practices for creating these calibration scripts? First of all, you need to take a statistically significant set of static images. Don't move your target around. Put your camera and your target on a tripod. Take one picture or 30 pictures. Move it to another spot so you don't have motion blur, and that you're also taking enough images that you account for the image noise. You should always cover the region of interest completely. When you're doing intrinsic calibration, make sure that you have images clear to the edge of your field of view, because extrapolation out beyond where you have data is going to be much worse behaved than interpolation where you do have data. I already told you not to tilt your target unless you're accounting for that. And do not count on your residual error to indicate that your calibration is good. It's an indication that it's bad if it's large, but as I said, if you just took all your intrinsic calibration images in the center of the image, you could have really low residual error, but your actual calibration would be poor. Always use high-quality targets. If you have a NIST traceable target, that would be great. They're very expensive. They're also very small and hard to use for a lot of applications. And then, if not, then calibrate your target if possible, and make sure that it lays as flat as possible, because those you can see errors in your image that you can see better with a camera than you can print with a printer is the issue, I guess. Okay, so here's an example that is part of the tutorial set at this point. In this case, it's simply 2 ASUS cameras looking at a 4x8 sheet of circles, 20 by 40, and again, it just runs by taking just a single image, which is against my recommendation, but at least an example that you can see that's in our repository at this point. It's easy to set up as long as you have 2 ASUS cameras and the package installed. And so what you saw happen was it took these two pictures on the left-hand side and then minimized the reprojection error and found out where the two cameras were. And if I had my pointer, you can see there's a camera on the left and the right, and they've been updated to their new locations. There's another tutorial online that's complete, where all the images are already collected, and you can see that. It's called Calibrate from Launch, and this includes 8 cameras, 4 on each side. They're on 2 different towers. There's 4 on this side, 4 on that side, and the idea was that an object was going to be passed in between them. We were going to collect 3D data, and then it was going to pass into a paint booth to paint the objects. So you can see the actual images from that, and it takes all the images, and each camera sees a certain portion of the target, and so it's a kind of an interesting example, but it's complete. It's all the information is there, and so I already talked about that other calibration, so I think I'm ready for questions. Okay, so I'm in the middle of about a year-long internal research project to do exactly that, and so the method that I would I guess I should repeat the question is, how do you tell when I suggested that you can't tell that the calibration is good just from residual error being small, and the question is well, how do you tell when it's good? And my answer to that is the residual error has to be small, but also and it turns out that Ceres provides this information, is it looks at the Hessian matrix. When you reach the bottom of the hill, is it concave up or is it concave down? So it does tell you a covariance matrix, and so you can look at that, and that's one of the things we're going to be adding soon, at least we're supposed to, is an indication of how good is the calibration. So that, and we also have a system which takes all the results and then tries to predict based on the geometry of all the observations and does a statistical model from the sequence of things that happened and creates a heat map of the calibration results of how good, basically it creates a covariance. Again, it's like a covariance for each of the different cameras and each of the different targets based on the information that was measured. Okay.
Yeah, I just wanted to ask, well, first of all, I want to say this is really, really awesome, so thank you. And the other thing I wanted to say was, is there a way to, a mechanism by which you can kind of vary how much robustness you need, how many targets you, or how many images you take, the statistical sampling, versus how well you can actually locate the object? So that way, if you need to compute very quickly, a rough area where the object is, you can.
Okay, so the question is how do you design, essentially, how do you design the calibration set of images to ensure that you have a good enough set to meet your design requirements? And I don't yet know how to do that. I do think I have a handle on, if you give me a design, I can analyze how good the solution is, but I don't know how to add a new, where do I move that next measurement to next best measurement in order to improve it in the right way. I haven't been addressing that issue at all. So the question is how much overlap do you need? And I mean, it's a complex, there's a complex answer in that I can calibrate 6 or 7 cameras that have no overlap if I have a calibration target on a robot and it puts it up here to this camera and then one up to here and then one to there, and I'm using the kinematics of the robot to sort of account for the fact that I'm not able to see the whole target. In the 8-camera example, no camera sees the same scene, but they're all attached to a physical, a rigid object that I know where the points are. So that's how we're calibrating that in that case. There was very little overlap in the images. It depends on the situation. It always depends on the situation.
All right. All right, one more.
Do you know how much of a performance hit you get from using automatic differentiation?
Okay. I do not know how much. The question was how much performance hit is there from using automatic differentiation, and I want to stress that series automatic differentiation is not numeric differentiation. Okay, it is finding an analytic Jacobian from the templated cost function. I'm not sure how that works, but I'm really happy it does because I've spent a lot of time writing Jacobians in the past and they're not fun. But I don't know how much of a hit there is computational. I just know it's not a really long process to compute a for what we're doing, it's plenty fast. It's very fast, so.
It's resolved compounding. Like the automatic differentiation, it's resolved compounding.
I'm not a computer scientist, but it's a genius who made it up, so.
All right, with that, thank